Well, hi everyone. I am not coming to you from my usual big massive whiteboard at Cal State Fullerton. Just wanted to give you a lecture a little bit more, I guess, personal style. I have a little tiny whiteboard here and I'm going to try to make this work. And I'm going to try to talk to you about section 8.2. I hope this is readable from your vantage point. The topic of this section is nth order linear constant coefficient homogeneous differential equations. That's an awful lot of assumptions about our differential equation. As I've said many times, most differential equations are impossible to solve. However, if we put enough constraints and enough conditions on those equations, turns out we can actually make some headway and try to solve for the unknown function in those differential equations. These equations here, linear, constant coefficient, homogeneous differential equations, are just such a family. It's a family of differential equations that no matter what, we can always solve them. So let me run through how we do that, and that's the whole idea behind this section. It's relatively easy to carry out in practice. So it's going to be something, I'm just going to experiment with this little whiteboard and see if I can explain it, okay? So remember that our differential equation is usually written as L of y equals 0. And the goal is to solve for y. And in this particular section, 8.2, I'm going to assume that my L, remember L is just an operator. It's just an operator that involves derivatives. So I am going to assume that it is just the operator a naught d to the n plus a1 d to the n minus 1 plus dot 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 plus all the way down to a sub n. So this is our usual polynomial expression for this operator L. So remember that the capital D just means that we are taking derivatives. Okay, so the number of derivatives is just the power of D that you see here. And I'm assuming here that A0, A1, A2, all of those coefficients are just constant numbers. I'm going to make that assumption. So it turns out that we can always solve this type of differential equation. It's homogeneous because of the 0 on the right-hand side. The coefficients, which are the a's, those are assumed to be constants. Okay, this is certainly the format of a linear operator. And so this is exactly what we're talking about. The order of the differential equation, that's just n in this case. Okay? How are we going to solve these differential equations? Well, what we're going to do is we're going to come up with a guess. We're going to take a stab at it. We're going to guess something that might work, and then we're going to see if we can make it work. And the guess that we're going to use is the following. We're going to try to take y equal to e to the rx. Now, that's a guess. It's sometimes called a trial solution. And what you can do with that trial solution is just take enough derivatives of it, so that would be n derivatives of it, so that you can plug them into your differential equation. So for example, the first derivative, well, that would be r e to the rx. The second derivative of y would be r squared e to the rx, and so on. And I hope my handwriting is okay. This is a pretty flimsy little board that I've got. But if we keep going like that, the nth derivative of y would just be r to the n times e to the rx. Okay, so we've calculated our derivatives. Let's go back and let's plug all of those derivatives into this differential equation now. So how is that going to look? Well, we're going to get a naught. I'm going to just write it underneath the operator L here. N derivatives of y is going to be r to the n e to the rx, right? That's the first term. The next term, we have a1, and then we have a1 times n minus 1 derivatives of e to the rx, and so on. The last term at the far side over here is just a sub n times e to the rx. And all of that is going to be set equal to 0. Okay, I hope you can read that all right. It's a little bit sloppy, but every single one of these terms has an e to the rx in it. There's an e to the rx in every one of those terms. So what I'm going to do, I'm going to factor out that e to the rx. Okay, I'm going to factor it out and see what happens. Okay, so let me give myself a little bit of room up here to write down what would happen if I factor out e to the rx. Okay, then what will happen is I'll get a naught r to the n plus a1 r to the n minus 1 plus dot 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 plus an. All of that is still equal to 0. Okay, still equal to 0. Of course, e to the rx is never 0. So what we can conclude, guys, is that for this r to work, I'm trying to find out which values of r will make e to the rx a valid solution to my equation. What I figured out is that if my r is going to work, it has to satisfy this equation. And this equation is just the same equation as what I wrote for L here on this line right here. Right? Except all of the d's have been changed into r's. Right? All of the d's have become r's. So when we're trying to solve, let me give myself a little bit more space here on this little board. Okay? When we're trying to solve for what values of r will make e to the rx a solution to our differential equation, which is L of y equals 0, right? This is what we're trying to solve, right? What we have figured out is that, well, as long as r satisfies this equation right here, a naught r to the n, right, plus a1 r to the n minus 1, and so on, dot, 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 plus an equals 0. Any value of r that satisfies that equation will work as a solution when I plug it in for e to the rx. This equation is called the auxiliary equation for the differential equation. So it's the auxiliary equation, and quite honestly, the thing that's the hardest about this is just finding the roots sometimes. I mean, if n is only 2, then it's just a quadratic equation, and of course we can solve that. But if n is bigger than 2, we might have trouble solving for the roots here. In some cases, the L might be given to us in a form that's already sort of semi-factored. And in that case, we won't have to struggle so hard to find the roots. I'm going to do an example in a minute to sort of show you what I mean. But in practice, one of the harder aspects of this, when you don't have a computer or a calculator in front of you, is just to find the roots of that auxiliary equation. Okay, but anyway, the auxiliary equation is easy to write down. We just have to take the capital D's that were in that original form of our differential equation and change them to r's. When we do that, we get the auxiliary equation. Okay, so I hope that so far this is making sense. Of course, a polynomial like this of degree n is going to have n roots. So we have some promise of some hope of coming up with some solutions to our nth order linear constant coefficient differential equation. Okay, let's try an example. Let me see if I can put an example on this little board for you to take a look at. Suppose I ask you to find, let's try to find the general solution, to, let me give you an equation here. It's going to be the quantity d minus 2 times d squared plus 16, d squared minus 16. So d minus 2 times d squared minus 16 of y equals 0. Okay? This is an operator that actually has already been partially factored for us. And so it's going to make it easier for us to get the roots. Technically, this differential equation is a third order differential equation. If you were to multiply out all of the d expressions here, you would actually get a d cubed. Now that's 3 derivatives, right? So this is really a third order equation. It means that the auxiliary equation is going to be a third degree polynomial. It's a cubic equation, which we have to factor to get the roots. Luckily, it's already been partially factored for us. So my auxiliary equation, remember, it's really easy to write down the auxiliary equation. You just change all of the d's to r's. So r minus 2, r squared minus 16 equals 0. And what we have to do is solve for r. And there are 3 values of r. In this case, because it's been partially factored for us, it's very easy to get those roots. Okay? Just 2, 4, and negative 4. Well, that means that we have 3 solutions to our differential equation. We have y1 of x, which would be e to the 2x. Right? So we have that solution. Then we have y2 of x, which would be e to the 4x. And we also have y3 of x, which would be e to the negative 4x. Okay, so that's pretty simple. And of course, remember that a third order homogeneous linear differential equation has a solution space, right? The solutions to that form a 3-dimensional vector space. So for an nth order linear differential equation, right, remember from section 8.1 that the solutions form an n-dimensional vector space. So we know that because this is a third order example here, that the solutions have to form a 3-dimensional vector space. Well, I've got 3 solutions here, and it turns out that they are linearly independent. You remember how we check that? Yeah, we can use the Wronskian. Remember the Wronskian that I talked about? The Wronskian of these 3 functions, e to the 2x, e to the 4x, and e to the negative 4x, that Wronskian, if you calculate it, will not be 0. Okay, that Wronskian will not be 0. So these functions are linearly independent. I'm asking you to kind of take my word for it, although we're going to do a group work. There's going to be a group work where you're going to be able to show that any time you get 3 distinct roots for the auxiliary equation, 3 different roots like we have here, then e to the power of each of those roots, right? If the roots are a, b, and c, e to the ax, e to the bx, and e to the cx are always going to be linearly independent. The Wronskian can show us that that will always happen. Okay? For now, I'm going to ask you to take my word for that, but we're going to do group work where you're going to get a chance to explore that using the Wronskian. If you believe me that these 3 solutions are linearly independent, then they must be a basis for our solution set. And if they're a basis, then we can write down the general solution to our equation. This is what the problem is asking. Find the general solution to this equation right up here. And I claim that we can do that at this point because we have 3 linearly independent solutions. So what's the general solution? Well, it's just going to be y of x equals c1 e to the 2x plus c2 e to the 4x plus c3 e to the negative 4x. That would be the answer to this problem. Okay? So there you go. That's the basic idea behind it. Okay? Let's practice one more example. Okay? Again, you can always pause and rewind if anything here is not clear. Let's try one more example of this, and then we'll go on a little bit. Okay? So let's do one more. Let's find the general solution. I wish I had a slightly less thick marker. This is kind of difficult, but I'm doing my best here. Okay? Find the general solution to, okay, this time I'm going to give it to you in the prime notation. So y triple prime minus y double prime minus 30y prime is equal to 0. Okay? Of course, if we want to write that in our operator notation, the way it would look would just be 3 derivatives is d cubed, 2 derivatives is d squared, and then 30 times 1 derivative is just d. All of that of y equals 0. So these are just two different ways of writing the same differential equation. The first way is sort of the classic way, just using the prime notation for the derivative. The second way is our fancy operator expression, where we use the d as an operator. And of course, from the d expression, from the operator expression, I can get my auxiliary equation very easily, right? My auxiliary equation, I just change all of the d's to r's. So it would be r cubed minus r squared minus 30r is equal to 0. Now on this one, we're kind of going to luck out a little bit because each of the factors on the left side has an r in it. So we can actually do the factoring ourselves. We can take out an r, and of course what we're left with is only a quadratic equation. So I can now take the quadratic equation and just factor it, right? I can just factor that thing. So this is going to be r times r minus 6 and r plus 5 equals 0. And so my roots this time are 0, 6, and negative 5. And if I know that if I have three distinct roots, again, I talked about this just a minute ago in the last example, if I have three distinct roots, I can write down my general solution. So let me see if I can put the answer here at the bottom of this little screen, right? So y of x is going to be c1 times e to the 0x, right? So I don't have to write that down because e to the 0 is just 1, plus c2 e to the 6x, this is very hard to write, plus c3 e to the negative 5x. So hopefully that is readable. That is the solution. Okay, so the different r values are showing up as the exponents of the general solution. Okay, so this seems easy enough, right? There's not too much trouble here. We just take the operator version of our differential equation, turn all the d's into r's, factor the auxiliary equation, get the roots, and write down the answer. The trouble is there are a couple of issues that can come up. There are a couple of issues that can come up, and I want to address both of these a little bit. So there are sort of two issues that do sometimes arise with this. The first one is you could get repeated roots to the auxiliary equation. So repeated roots. So let me say a quick word about this. This is not too hard to address, but again, you have to sort of guess the remedy for this problem. So in other words, when you get a repeated root, that means you're going to not get as many different r values, right? So if some of the same roots are showing up in the auxiliary equation, then you're not going to get as many r values, and then you're maybe not going to get enough r values to create n terms to build your general solution, right? Remember, it has to be an n-dimensional solution space. So what are we going to do if this happens? Well, let's suppose, for example, that a root r, so let's call it r, if r is a root, and let's suppose that it is repeated k times. So let's suppose we get the same root over and over again, several times. Let's say k times. So we have a particular root r here. Well, it turns out we can still get k linearly independent solutions to our differential equation that are all associated with that particular r value. So this r can be used to generate enough solutions, right? So if this happens, if r is a repeated root, and it repeats k times, what we can do, guys, is we can form k solutions. So what are we going to do? Well, the first solution is just going to be, e to the rx. Nothing strange there. But how are we going to get additional solutions that are associated with the same r value? I can't write down e to the rx again, because that won't be linearly independent. Right? That's not going to give us a linearly independent basis solution. Turns out, and it has to be checked, but this has been discovered once in the history of the subject, doesn't have to be reinvented ever again, that if you stack an x in front of e to the rx, this is not a scalar multiple of e to the rx, right? This x that's in front here is not a number, it's not a particular constant. And so this is actually linearly independent from e to the rx, and what's more, it actually is also still a solution to our differential equation, our nth order constant coefficient homogeneous differential equation. And what do you do if you have even more repeats of that same root? If we need a third solution, well, we just stack another power of x in front of that e to the rx. And we just, as it turns out, we just keep going like that. We can actually get all the way to k additional solutions here. K additional solutions. And the kth one, as you might be able to figure out from the pattern, is just x to the k minus 1 e to the rx. So this is how you handle repeated roots, the first of the two issues that I want to go through with you. If you get a repeated root r that shows up, let's say, several times, k times, then you're going to make k solutions by just starting to stack those x's in front from one solution to the next. You just throw on an additional power of x each time. Okay, so that's pretty simple. That's the first issue, and that's kind of how you handle that. Let me, again, if you need to pause this or watch any of it again, feel free to do so. Let me move on, though. I'm going to erase this so that I can talk about the second issue that sometimes comes up. The second issue that we have to deal with is the issue of complex roots. Complex roots. So, of course, your auxiliary equation could have complex roots. And the question is then, well, how are you going to deal with that? So suppose that we have a pair of roots that are complex. Let's say a plus or minus ib. Okay. Well, the problem is, you don't really want to write down a solution that looks like this. You don't really want to write, a plus bi times x as an exponent. This would be e to the rx. But having an I in our answer is a little bit unsatisfying because it tends to be difficult to understand. Like I wouldn't know how to graph it, for example. It's very hard to evaluate it unless you have a whole theory of complex numbers. And in fact, it really doesn't form a nice, real solution. So we're not going to be able to just leave it at this. Okay? It turns out that the way to address this is we have to somehow figure out how to take e to a power that has I in it. And it turns out that there is such a formula, and you maybe have seen this before. E to the I theta, it turns out it can be expressed in terms of cosines and sines. It's the cosine of theta plus I times the sine of theta. Okay, this is called Euler's formula. It's a very famous formula that expresses an exponential function in terms of sines and cosines. And it can be proven using power series expansions. That's a typical way to do it. You write down the power series expansion for this e to the I theta. You write down a power series for the cosine of theta and for the sine of theta. And you look at the left side and you look at the right side and you realize that the power series are the same on both sides. So this is a valid equation right here. If I'm allowed to use that equation it's going to make it easier for me to take this y of x right here and get rid of this imaginary exponent. Because you see what I can do right here. I can come back up here and I can write this as e to the ax times e to the I bx. Right? So if I think of the theta as being b times x, well, now I've got a way of using the Euler formula to simplify this. So let me go ahead and actually use that Euler formula right now. This is just going to give me, right? This is just going to give me e to the ax times, right? Times, well, it would be, according to the Euler formula, the cosine of bx plus I times the sine of bx. Okay? And sorry about that. It's just hard to write on this board, but that's the expression. Okay? Now, I still have an I in this expression. It's not good enough, right? I'm still not happy with that. But at least it's not in the exponent anymore. And it turns out, I'm not going to go into all of the details at this very moment, but if you go back and you repeat this same calculation using a minus bi, you're going to get another solution corresponding to the root a minus bi that looks very similar to this one, except it has a minus sign in the middle. Now, if I have a real term plus I times an imaginary term, and then I have another solution where everything is the same except a minus in between them, then what I can do is I can add those solutions together. I can just add them together. If I add them together, so like in other words what I'm saying is if I have another solution here, which is e to the ax times the cosine of bx minus I times the sine of bx, I could add these two solutions. And if I did that, I would cancel the imaginary part. I would cancel the imaginary part completely. And remember that we're talking about a subspace here. The solutions to our differential equation are closed under addition. So I can take these two solutions, both of which have I in them, I can add them together, which cancels the imaginary part, and leave myself with just the real part. And it's really 2 times the real part, but I can also multiply by a 1/2 if I really want to, and scale it back down so that I actually obtain just this guy right here as a solution. Isn't that great? So we get a real solution that has no imaginary numbers in it. The a and the b from the complex root are showing up in the exponential and the cosine parts specifically. We also, instead of adding the two solutions, if we subtracted the solutions instead and then divided by the 2i, we would get another solution which would be e to the ax times the sine of bx. The upshot is, guys, when we have a pair of complex conjugate roots, we're going to get two solutions that are expressed in terms of sines and cosines. So the two solutions, let me just write them down so that they're up here in front of you. Right? The first solution, y1 of x, is just e to the ax cosine of bx. And the second solution, I'll call it y2 of x, is e to the ax sine of bx. Okay? By the way, if you have that same complex conjugate pair more than once, if there's repeats of the complex numbers, we can go on, right? And we can write down additional solutions. Let's say that the root a plus or minus bi repeats 2 different times. All we have to do again, guys, is stack those x's, just like I explained before. So if you stack the x's in front of these expressions, this is what you would get for your third and fourth solution, if I can possibly write it in a legible way there. Okay? So there you go. There's the solutions in the case of repeats of complex numbers.